everyone. Welcome to the second chapter of A2 physics lecture, which is gravitational fields. We have studied about three fields in O levels in physics, which is gravitational field is one of them, and there was magnetic field, and the other one, if you remember properly, is electric field, right? So these are the three fields that we have studied in our O level physics. Out of which the first one now we will be discussing in A levels is gravitational field, A2. Electric field we have already discussed in AS physics, and the magnetic field also we will be discussing in our A2 physics. So in A2 we will be covering, out of three we will be covering two of them, the gravitational field and the magnetic field. So what is gravitational field? You have the basic idea. It's not that it's completely new to you. You know what a gravitational field is. How does a gravitational field work? What does it do? That is known to us. Okay, so the very basic thing, what a gravitational field is. So it is a space around any mass. Okay, so let's take a mass capital M. So it's a space around any mass where it can exert a gravitational force on another mass. Let's point another mass here, place another mass, small m. So this small m will be attracted towards this m due to the gravitational force. Likewise, the larger mass of the capital M will also be attracted towards the small mass with the same force. Okay, so from Newton's third law we know that the gravitational force acting on this mass and this mass is equal. So the easiest example is the sun and the earth. So if this is the earth and this is the sun is attracting the earth with a force of F. The earth is also attracting the sun with a force of F. So both of these are gravitational force. So the sun and the earth, they are inside the gravitational field of each other. That's why they can attract. Okay, maybe the sun is a bit further away from the earth, therefore it's not inside earth's gravitational field, because earth has a small gravitational field, whereas the sun has a much larger gravitational field. So the earth falls within the gravitational field of the sun. Now, why is the sun's gravitational field larger and the earth's smaller? We will discuss that later. But for the time being, let us just focus on what a gravitational field is. So gravitational field is basically what we call a space or a region of space around a mass where it can exert gravitational force on another mass. One mass can exert gravitational force on another mass inside a given space. That is what we call the gravitational field. We will come to the definition part later. Gravitational field, I hope it's clear. You have already studied about it in O levels. Now the next part which comes is gravitational field strength, or the gravitational force. Actually, we will talk about gravitational force first, and then we will go for gravitational field strength. What is gravitational force and how do we calculate that? Let us bring up a very easy example. Let's say this is the surface of Earth and you're standing here. Any person standing here. Now the earth is pulling this person down with a gravitational force of say 600 Newton, which we also call is the weight of the person, right? The weight of the person is 600 Newton, which is the gravitational force on the person. So weight acting on a person or any object due to Earth's gravity is basically the gravitational force acting on that person. So gravitational force is, when we compare the gravitational force on Earth or any other planet actually, the gravitational force basically is the weight acting on the person or on the object. How do we calculate the gravitational force from here? So gravitational force, what we have learned, if gravitational force is the same as the weight acting on the object, gravitational force can be calculated where? Using the formula m into g. The simple formula we have been using for a very long time, that the gravitational force or the weight acting on an object is found by multiplying the mass of that object. Remember, the mass is the mass of this object, not the mass of Earth. The mass of the object multiplied by the gravitational field strength of Earth. Okay, this is the gravitational field strength of the Earth. So that is how we calculate the gravitational force acting on any object. This is okay when you are calculating it for something which is placed near the surface of the Earth. Okay, it's very close to the surface of the Earth, then it's fine. We can use this formula because we can find out the gravitational field strength. The mass is known to us, we can find it. What if you try to find the gravitational force acting on the moon due to the earth. So this is the moon, this is the earth. The earth's gravitational field extends up to the moon and beyond it maybe. So there is gravitational force acting on the moon. I have given you the mass of the moon. Let's say the mass of the moon is m2, the mass of the earth is m1. If you tell me that now if I want to find the gravitational force acting on moon is equals to the weight of the moon, which is m2 into g. m2 is the mass of the moon and g is the gravitational field strength of the earth, which is the same formula as this one. Okay, that would work, but it would only work if you know the gravitational field strength of earth over here. You cannot take the field strength over here as 9.81, because as you go further away from the planet, the gravitational field strength gradually decreases. So if the gravitational field strength changes, you cannot have the same weight with the same formula. That's why we need to come up with a different formula when we are going further away from the earth. When the distance is increasing further and further up. That's why we can't use this formula when the distances are very large compared to the radius of the earth. Okay, so the radius of the earth itself is very large. Now if you go further away from the earth, which is larger than the radius of the earth, we can't use this formula because the gravitational field strength's value changes quite prominently, right? So we can't use that value over there. All right. So as we were discussing that we should come up, or we need to come up with a different formula to find the gravitational force acting on an object when the distance is quite large from the surface of the planet or from the surface of the star or whatever astronomical unit distance you talk about. So let's say this is the planet Earth, this is the center of Earth, and the radius of Earth is given r1. Okay, r1 is the radius of Earth. Now when we are considering the gravitational field strength at the surface of Earth, we consider it as 9.81 Newton per kg, okay, at the surface. Now, if you go the same distance above the surface of the Earth, if this is say 6,500 kilometers, and you go another 6,500 kilometers above the surface of Earth, you cannot say the gravitational field strength will remain the same. Okay, so the gravitational field strength will decrease as you go further above the planet. So if I tell you to find the weight of an object at this point, you can use the formula W equals to m into g, but in that case you have to know the value of g at this point. So that is difficult to find. Rather, we have another equation which can be used to find the force acting on the object at this point, which is twice r1. Okay, so even if we go very far from the planet, we can still find the gravitational force acting on the object, which is the weight of the object also. So according to Newton, this is called Newton's law of gravity, where he discovered the formula for the gravitational force acting on 2-point masses. Now Newton found it out for 2-point masses, very small point masses, let it be electron, proton or an atom, doesn't matter, but it's very small. Okay, so 2-point masses, this word is important, you have to write it down in your definitions also, that the gravitational force between 2-point masses is directly proportional to the product of their masses. Like if you have an object here, the mass of the Earth, and if the moon is placed here, m2 is the mass of the moon. So it's the product of m1 and m2, and it's inversely proportional to the square of the distance. So if I have a planet here, let's say this is Earth, this is moon, the mass of Earth is given m1, the mass of moon is given m2. So you multiply the mass of these two objects together, and then you divide by the distance between them. The distance is found from the center of the moon to the center of the Earth, and you just don't divide the distance, you have to square it. So what do we get from this two equation? Let's say if the mass of any one of the object increases, let's say if you could increase the mass of the moon somehow, if the mass of the moon could increase, the gravitational force between both of them would increase, because we have already discussed this, that the gravitational force acting on the moon due to Earth and the gravitational force acting on the Earth due to moon is equal. So if you increase the mass m2, the overall gravitational force between both of them will increase. Also, if the distance increases, the gravitational force decreases using inverse square law. That means if the distance is doubled, the gravitational field strength becomes 1/4. So if according to this equation, if we come back here, when you have doubled the distance, the gravitational field strength over here, or sorry, the gravitational force over here should become 1/4. Not the strength, the gravitational force should become 1/4 of what was here. So if the gravitational force here on the surface of the earth, you found the gravitational force to be 100 Newton, it should become 25 Newton here. It should become 1/4 because the distance is double. The first distance was taken from the center of the earth. The second distance is the double of that distance. So the force becomes 1/4. Okay. So that is what these two equations tell us. So from Newton's law of gravity or gravitational force, we say that the gravitational force acting between 2 point masses is m1 and m2, the product of the masses, and is inversely proportional to the square of the distance between the two masses. Now the question comes, if this is for 2 point masses, how can we use it for planets? Because planets are not point masses, they are huge. They cannot be considered to be point masses at all. But why do we consider it? This is because this is also a question that you will face in your question paper. The diameter or the radius of the planet is much smaller compared to the distance between them. So if the radius of this planet is r1 and the radius of another planet or a satellite is r2 and the distance between them is r, this r, that is the distance between them, is much greater than the radius of any one of the planets. So the distance is so much large that we can consider each of this object to be point masses, because the value of the distance between them is very large compared to the radius of each of the masses. Okay, so that's why we can use the same equation even when we are calculating the force on astronomical scale. Okay, so combining these two equations, that the masses are the product of the mass is proportional to the gravitational force and the distance between them is following inverse square law, these two equations combined gives us the force acting between 2 point masses. The gravitational force can be found using F equals to g m1 m2 by r square, where g is a constant which we call the gravitational constant, and the value of g is given 6.67 10 to the power minus 11, and if you find out the unit, it's Newton meter square per kg square. So that's how we find the gravitational force acting between 2 point masses, even if we don't know the gravitational field strength of that particular point. So there might be questions, or there might be situations where you don't know the gravitational field strength due to a particular mass. Maybe Earth, their gravitational field strength you don't know at a particular point, but you can still find the gravitational force acting on another mass placed here just by knowing the mass of that object, knowing the mass of the Earth, and then using the distance acting between them. Okay, if I tell you to find the gravitational force caused by a stone, even a stone has a mass, right, at a distance r on another stone which has a mass m2, you can still use this equation, but you have to make sure the value of r is much larger compared to the radius of the stone itself. Only then we can consider them to be point masses. So this is how we can find the gravitational force acting on two different objects with masses, and when we know their masses and we know the distance between them. Okay, so I hope that clears out how we find the gravitational force. The next part we will talk about gravitational field strength. What is gravitational field strength and how do we calculate that gravitational field strength? Okay. Alright, so before we move on to the gravitational field strength, there is one more thing that we have to discuss, is how do we calculate the time period of a satellite when it's moving around a planet or orbiting a planet. Not only for a satellite, any object when it's moving around a object, another mass, how do we calculate the time period for that? That is what we will derive from here. Okay, so in the previous chapter of circular motion, we know that any object when it's moving in a circular path, there is a centripetal force acting on the object. And if you recall the formula for centripetal force, it was mv square by r, where r is the radius of the circle, mass m is the mass of the rotating object, and v is the linear velocity. So here we have a situation where we have a planet and a satellite orbiting the planet. The satellite can be an artificial satellite, a natural satellite of the planet, does not matter. It's a satellite orbiting the planet around it. Now, we know the mass of the satellite, we know the mass of the planet. This is given by small m, this is given by capital M. So we know as the satellite is orbiting around the planet, at any particular point there is a centripetal force acting on this particular satellite towards the center of the planet. And if we find the radius or the distance between them, the radius is given by r, right? Let's say it's r. So it doesn't matter at whichever point you find it, it's r, right? So we can find the centripetal force acting on this satellite using this equation. So we write the centripetal force, which is mv squared by r. Also, we studied in circular motion that the centripetal force acts on the satellite because there is a gravitational force acting between them. So the gravitational force acting between the planet and the satellite is providing the centripetal force. So we can say this centripetal force is actually coming from the gravitational force acting between these two, which is equal to g m by r squared, where m, small m is the mass of the satellite, capital M is the mass of the planet, r squared is the distance between them. So these two are equal. Okay. So we try to solve it out and try to find the time period of the satellite. If we start solving it, the first part what we get here is m gets cancelled out. The mass of the satellite is completely irrelevant, it goes out of the equation. The next part, we have 1r and 1r getting cancelled out here. So you're left with v squared equals to gm by r. Again, if you recall from the circular motion chapter, the linear velocity was found using the equation 2 pi r divided by t. So why we use 2 pi r here? Because the 2 pi r, okay, as I was saying, because the 2 pi r gives the circumference of this complete circle. Alright, so linear velocity is the distance it's traveling since it's completing a complete circle. So 2 pi r gives the circumference of the circle, and t is the time period of the orbit. So t is what we want to find here. What is the time period? So we have a v square here. If you square it, if you make it a v square, you get 4 pi square r square divided by t square. Put it back here, you get 4 pi square r square divided by t square equals to gm by r. So if you make t square the subject from here, you eventually come up with the equation. I'm just shifting it here. T square is equals to, it's 4 pi square r cube divided by gm. 4 pi square r cube divided by gm. Now look here, if you carefully look at this equation, this 4, then pi, then g, and then m, these are all constants, right? 4 is a numerical value, pi is a numerical value, there is no change in them. G is a gravitational constant, the value is fixed, and m is the mass of the planet. So the satellite is orbiting the planet, the mass of the planet is not going to change, the mass of the planet remains the same. So we can say this entire part is a constant. So that gives us an idea or a relation between the radius and the time period of the satellite. So if the satellite, if you take the equation, t square is proportional to r cube, or t is proportional to r to the power 3 by 2. So the time period of a satellite is proportional to the radius to the power 3 by 2. So the further you place the satellite, the longer it will take to move around the planet for a particular speed, which is obvious. If you place it further from the planet, it will take longer to move around because it's not going to cover the same distance. The distance also increases, the circumference is increasing. If you increase the radius, the circumference increases, it takes a longer time to cover the same distance, right? So that's what is shown by this equation. So this equation you have to prove at times in your question paper, that t square is proportional to r cube. And how do we prove it? This is how we derive this equation. So we start with the centripetal force and the gravitational force acting on each other. You have to state that in your answer first, that you have assumed that the centripetal force is provided by the gravitational force acting on the satellite, and then from here you will have to show the steps, and these are the side notes which you can get. Okay. So We'll keep it up to here, the time period of a satellite. In our next videos, we will be discussing about gravitational field, and we will be finding more questions where we can solve them. So I hope this will help you out in the next video.